Okay. Okay. So Nicholas is a third-year PhD student at TU Berlin at the Security and Telecommunications Chair with Jean-Pierre Seifert. His research interests lie in foundations of cryptography, quantum computing, and learning theory. In particular, he's focusing on quantum advantages for learning and optimization tasks. Let us all welcome our speaker.
Yeah, thank you very much for the kind introduction. So my talk today is about our most recent work. It's a joint cooperation of the TU Berlin and the FU Berlin, two Berlin universities, with my colleagues Vincent Ulich, Frederick Wilde, Jens Eisert, and Jean-Pierre Seifert. And the title is a super-polynomial quantum advantage for combinatorial optimization tasks. So if there's one message that I want you to take away from this talk, then it's that quantum computers can provably approximate combinatorial optimization problems better. And so there's a few keywords. The first one is provably. So we actually provide a proof that there are instances where a quantum computer can outperform classical computers for the task of approximating combinatorial optimization problems. So what are combinatorial optimization problems? Let's look at the very prominent example, which is the graph coloring problem. So in the graph coloring problem, you're given some graph with nodes and edges, and the task is to color the nodes such that no nodes have the same color that are connected through an edge. So this one in the top here is red. This is blue, the other one here is also blue, this is also blue, so they don't share the same color. Mathematically, you could describe your color with like an integer, and the task is to find a valid coloring of this graph with as least colors as possible. Now this problem can be taken to solve many different problems in the industry and that are practically relevant, for example, aircraft scheduling or assigning GSM frequencies in your mobile network, or basically finding an optimal student timetable or booking for the booking of rooms. Also for machine learning tasks, it will be interesting because many image segmentation tasks can be cast into this graph coloring problem. And also if you have multiple surveillance cameras, finding a perfect camera coverage is also a graph coloring problem, essentially. And then you can cast these combinatorial optimization tasks often in the form of an integer linear program. So in an integer linear program, you're given some minimization or maximization task over some variables like here wi, and then you have some constraints that basically encode your problem. These constraints are linear. And most combinatorial optimization tasks are NP-hard. And it has also been shown already many years ago that also the approximation of these combinatorial optimization tasks is NP-hard. Sorry. And so there's not really, we cannot reasonably expect a quantum computer to solve these problems or even like approximate it up to a very close, very closely, because that's NP-hard. But the question arises, can quantum computers do better than classical computers in this approximation task? And so here in the lower right, we have this picture where we are giving this optimization task with a classical computer, and we have this j of x, which is our cost function we want to minimize. And with a classical computer, we find that j of x is 10. But if we take a quantum computer to aid us, we find that j of x is 5. And so before our work, there was not even a semi-reasonable super-polynomial advantage for a quantum computer to outperform a classical computer in this task. So our work really constitutes a in principle result, but it is proven that there is a super-polynomial advantage. So where does our work lie in this Venn diagram? We see the set of integer linear programming instances, ILP instances, and the blue clouds here show show instances that are classically hard, and the yellow clouds show instances that are quantumly efficient, or that you can solve or approximate quantumly efficient. So our work really lies in this intersection here, where it's classically hard to approximate, but it's quantumly efficient to approximate. Okay, so to show a quantum advantage for this kind of task, we need two things. We need the classical hardness, and we need quantum easiness. So we need a class of instances that are classically hard, but at the same time quantumly easy. So how do we do this? On the classical side, we use tools of cryptography to show first the hardness of some learning task, and then using the very famous theorem of Occam's razor, we can derive from this hardness of learning a hardness of approximation. And then with some tricky reductions, we can derive we can come up with reductions that transform this hardness of approximation also to a combinatorial setting, where we now have the hardness of approximation for a combinatorial optimization task. So what I'm going to talk about today is, first of all, I want to give you the background on the hardness of the learning first. And it will require some learning theory, which we will get into in a few minutes. And then using the theorem of Occam's razor, we will derive we will reason that it follows a hardness of approximation. And once we have this set, we will take a very brief look into cryptography to get instances that are hard to learn. And then for the reduction to a combinatorial optimization task, I didn't focus too much in this talk. It's a little tricky. You can read it up. It's like known results from the 80s. Yes. And on the quantum side, basically what is our quantumly efficient combinatorial optimization algorithm? Basically, it's Shor's algorithm. We use Shor's algorithm to break the cryptography in the very beginning of these reductions and show that then we can walk down these reductions and come up with a quantumly easy, with a instance that approximates these ILP instances very well. Yeah, so it's basically thanks to Shor's algorithm. And this is where we lend our super-polynomial advantage. Okay, so let's jump right into this hardness of learning. So we need a few definitions here. They're very simple. Basically, what we need are a concept class. A concept class is something that we wish to learn. Concept class mathematically is basically just a set of functions that map from n bits to 1 bit. And basically what you can think of a concept class or some concept in a class if you take, for example, as input an image, which is represented as n bits, an n-bit string, and you want to say, is there a cat in the image? And then this is the question, and your the concept class will tell you there is no cat or there is a cat, either with 0 or 1. And this is the kind of mathematical objects that we want to learn. And we want to learn that using a hypothesis class. So we pick some class of, again, these kind of functions, and we wish to optimize over these hypotheses to get close to our target concept. So what we get, what is here described as a labeled sample, it's basically your training data. I will in the rest of the talk say that this is S. And S is basically just a list of inputs like x1 and a label according to the concept that you want to learn. So x1 and C of x1 up to m samples. Okay, and then there's really the backbone of the learning theory world is the probably approximately correct learning. And for short, sometimes it's you will read it often as PAC, PAC. And what it says is we pick two numbers, epsilon between 0 and 1 and delta between 0 and 1, and a PAC learning algorithm for this concept class C by an hypothesis class outputs some hypothesis such that some error is less than epsilon with probability at least 1 minus delta. And yeah, so the error basically you can say you can understand it as that there's some distribution D over your inputs, and you want to be, if you pick like some X from this distribution of the inputs, then it should be very close to your C when you plug it into H. Okay. By the way, if you have any questions, please go ahead and just interrupt me. Okay, so this is PAC learning, and then okay, this is like the backbone of the learning theory. So now we want to investigate this theorem of Occam's razor, but because it really connects now the task of approximation with the task of PAC learning. So let's first have two more definitions, but they're also very simple. So we say that some hypothesis H is consistent with our labeled sample. By the way, our labeled sample here, the sample is the whole list here. The sample is the whole list, and one pair of input-output I will call an X sample. Okay, this is sometimes a little tricky, but okay, this is how I will call it. Okay, so some hypothesis H is consistent with our labeled sample, so basically our training data. If for all the inputs or all the X's in our training data, we get the same label. So then H is consistent with S for all the inputs, but only on the training data. Okay, and then we will also need the definition of the size of our hypothesis. This will be like information theoretically very, very important. So let's think of some fixed encoding of our hypothesis, and we denote that as the size of H. And it basically gives us like a measure on the complexity of H. Okay, and so the theorem of Occam's razor, it basically tells you that if you're given a labeled sample S of some concept C, and it has this size. It's like n is equal to like O, and then there's something that's polynomial in 1 over epsilon and 1 over delta. So don't get too confused by this formula. It's not so important to understand this in this talk. But what's more important is that there's like some lower bound on the number of samples. And if you have sufficiently many samples, like n examples, then for some fixed alpha greater than 0 and beta between 0 and 1, if you can find any hypothesis H that is consistent with S, and S having the size n, and which satisfies that the size of H is smaller than the optimal size times some factor that is basically a polynomial in the optimal size and something that's less than the size of S, then this H satisfies that the error is less than epsilon with probability at least 1 minus delta. Okay, so what does this say? If we can find an hypothesis that is consistent with S, with our training data, and that is sufficiently small, then we can PAC-learn. So, and really this is an approximation task. Finding a hypothesis that approximates the optimal size by some factor that is basically a polynomial in the optimal size, and S and beta here is between 0 and 1, so it's less than the size of S. This is really the approximation task. And now to put this really in a problem where we can reason about the approximation, we can define the consistency problem. Yes.
I'm wondering, so what does optimal of H mean?
Yeah.
Because I feel it's like, okay, optimal maybe is the smallest size I can use to run, but then it's bigger than the H, so I'm confused.
Yeah, because the optimal, but it's times this factor. So of course your H cannot be smaller than the optimal,
okay.
but this factor here, it's greater than 1. So this H opt here is of course bigger than 1, and
Okay.
this S is also bigger than 1. So this factor is bigger than 1. So all of this this right side here is bigger than the optimal size. Okay.
Sorry, I have a follow-up question. How do we decide the optimal size of H? Is it given, or how do we know this? Or we just assume there is some optimal number?
This is a very open question. How do we find the optimal size? You can take any problem or like even come up with a circuit, and now finding a circuit that is optimal, it's a really hard task. There's no known algorithm that does this. There's some, like if you restrict your hypothesis class very much, then you can say something about the optimal size. For example, if you take a DFA, a deterministic finite automaton, as your hypothesis class, then you can then there's algorithms that probably minimize the size of the automaton while outputting or generating the same language, but these DFAs, they're very restricted. So if you want to have like a more powerful class of hypotheses, for example, take Boolean circuits or a Turing machine, then there's no known algorithm how to find the optimal, and it's really not known what really the optimal is. Yeah. So this is just information theoretically, this consideration. We do not really know what h-opt is. But for the approximation task or for our result, we don't really need that. We only need to be better than the classical.
I see. Yeah, thank you.
Okay.
Sorry, I have another question. So
Yeah.
the hardness here is using like the number of examples as a measure. It's because like it seems to me the outcome this razor is like if I satisfy this complexity, then I can solve this patterning problem or approximately. So it's regardless of my my hypothesis size.
So the hardness is like in this talk I consider hardness with like classical hard to do something. So there's only a exponential time algorithm. But I guess what you mean is why is what's the meaning of the M here, right? So the better you want to pack learn, so the smaller you want to get epsilon, and the smaller you want to get delta, the bigger the M gets. So you have to be, your hypothesis needs to be consistent with a larger sample. So this is like it gets the more accurate you want to pack learn, the more harder it will get because you need to be consistent with M samples.
So this I mean, then here we don't discuss like how complex my edge is to solve this problem. Or oh, hello, it's me. Hello.
Oh, okay. I think I'm back. Hopefully, can you hear me?
Oh, yes, yes.
Okay, perfect. So I think my internet had a hang up. So yeah, you had a follow-up question.
Oh, yes. So my question is, if this hardness, I think, I mean, to me here is like we use how many sample I need to solve this, but what about like how complex my my
Sorry,
edge
about what?
is?
How
complex my edge, like my model need to be to learn? I mean, is there a difference, or in this case we just assume just some model, whatever how complex it is, I can just use it? Is that true?
Yeah, so I mean, you can pick your small h from this big class of large h, and I mean, of course, if you want to, it really depends on the learning task, right? So if the learning is a really simple task, it doesn't matter how many samples you give me. I can always like classify them correctly, and also my model doesn't need to get more complex. But if your learning task is really complex and you want to be consistent with M samples, then as M increases, also the complexity of H will increase. So it's really dependent on the learning task of like a lower bound on your on H, on the size of H.
Okay, cool.
Okay, so yeah, so to pack this approximation now into a nice to handle problem, we define the consistency problem. So in the consistency problem, we are given a labeled sample S of some unknown concept. And the solution of this problem is some H, and H is consistent with S, and H must be minimal. So solving this problem exactly as we already mentioned, also thanks to the great question, it's a very hard to do finding really the minimal model. But what we want to do is we want to approximate this problem. Okay. So let's assume that we have some, let's assume that we have like a no-pack learning result, for some concept class C. Then by the theorem of Occam's razor, we can also say that it must be hard to approximate the consistency problem of the C. Because if we could pack learn, because if we could approximate, then we could also pack learn. So if we had a no pack learning result, we also know that approximation must be hard. Okay, and now we will get to this overview we already saw. We talked about the hardness of learning or pack learning. We talked about Occam's razor, and now we saw how we can derive from this the hardness of approximation. And so where do we get this hardness of learning? Basically, we get it from cryptography. And so I guess you're not too familiar, or I will assume that you're not too familiar with RSA. But in the RSA crypto scheme, there's basically two functions. You can encrypt and you can decrypt. And what you basically do is you take some message X. When you encrypt, you take it to the power of some public exponent E, mod n, and it will give you your encrypted message Y. And then to decrypt, you will take this Y, and you will take Y to your secret exponent D, mod n, oops, and it will give you back your message X. This is the basic RSA scheme. We don't need to understand it in detail. What's important is that we will take this Y to the D, and that this is basically the decryption. And so, like learning something about this X given Y, it must be hard because that's basically the cryptographic assumption. And also, what is hard is the least significant bit of X. Learning this is also hard, given Y. And so this now fits perfectly into our framework of a concept class, where we have a concept class now that goes over some secret keys D, and the label and an input to this concept class is some Y or some variation of Y, and the output is the least significant bit of X. And now this must be hard to learn. And we can put this into a nice bigger like framework of concept classes, which are Boolean circuits. And so below here in this picture, I have like sketched out a Boolean circuit that does this decryption. Basically, what you do is you get as input like consecutive powers of Y. So this is Y to the 1, Y to the 2, Y to the 4th, Y to the 8th, and so on. I just wrote the exponent here in binary representation. And then if you want to calculate Y to the D, some number D, what you do is you only multiply those inputs where the bit in D is 1. So if the first bit in D is 1, then you will multiply this. The second bit of D is 0, then I won't multiply this. So the third bit is 1 again, I will multiply this. And then everywhere where D is 1. I will multiply these, and by some simple calculation, basically what you do, you just add up these exponents if you multiply them. And then you can see that basically what you do is just y to the power of d. And so I will multiply them, and what I get out is then this x, which is y to the d. Let's write this again. And I can just take the least significant bit of this, because it's x. So this is x. And I can just take the least significant bit of this, and this will be the output of this Boolean circuit. And now learning this concept class, of course, is hard, but let's try to think about it in the Occam's razor setting now. What must be hard now is to come up with some other Boolean circuit, for example, output pairs of this here, and also approximately as small as this. And this must be hard to do. So basically it says that it is hard to come up with a small Boolean circuit that also does this, or that is consistent with some input-output pairs. Okay, so this is again the approximation task. So what we've done now, we've looked at hardness of the learning. We looked at Occam's razor. We see how a no PAC learning result, from it follows a hardness of approximation. And we've seen some example in cryptography, how we can get the hardness of learning, hardness of PAC learning. Then by Occam's razor, we know that the approximating, or coming up with a circuit that is very small, that approximates basically which size approximates the optimal size, must be hard. And so we get this hardness of approximation. And now this is very, very far from really what a combinatorial optimization task is, or what it means to approximate in a combinatorial optimization task. So really, I didn't focus on that too much, how you can now come up with a combinatorial optimization task, but I want to sketch this. I want to just hint at it, because so here in this graphic, we see the reasoning of how to find this hardness of approximating a combinatorial optimization task. So we started from the hardness to invert this RSA function, or this RSA circuit. We then know that it must be hard to PAC learn this circuit by some other Boolean circuit. And so now through Occam's razor, we can get into this regime of approximation tasks. And through Occam's razor, we know that approximating the optimal size of a consistent hypothesis must be hard. And then there's a few results, results from this reduction, that like any Boolean circuit, you can write this RSA function in a Boolean circuit. I wrote here CRSA. But you can also write this, then you can reduce these Boolean circuits to Boolean functions. So basically you flatten out your whole Boolean circuit tree into some function, a Boolean function. Then approximating the size of this Boolean function must also be hard by some consistent age. And then you can reduce these Boolean functions again to log space Turing machines and to deterministic finite automatons. And so we get really this hardness of this consistency problem for DFA RSA, so the DFAs that decrypt the this RSA ciphertext. And then you can go to, okay, if you cannot do it with any H, then you also cannot do it with some other DFA. And by this, and then there's a really nice result by Kearns and Valiant. Through this consistency problem, you can basically encode it into some problem that's called the formula coloring. Let's write this out. Formula coloring problem. And it's a really nice reduction that reduces this consistency problem, finding a consistent DFA that is finding a consistent DFA to some other DFA. You can write it as a combinatorial optimization problem of formula coloring. It is very similar to the graph coloring that we had in the beginning. Yeah, and then this is a combinatorial optimization task. And okay, and we can write this formula coloring also as an integer linear program. And so what we have now through this whole reduction chain, we now have found this class ILP minus RSA, so ILP RSA, which is basically a class of integer linear programs that are provably, where the optimal solution is provably hard to approximate for a classical computer under the assumption that inverting the RSA function is classically hard. Okay, and so what we come up in our paper then is like this huge integer linear program. It's not so important to look at all the details, but again, we have this minimization task over some variables and some linear constraints. Okay, and now the two central theorems in our paper are what we discussed the whole time now, the classical hardness of approximation for the integer linear program. So basically, we assume that the hardness of inverting the RSA function for a classical computer, then there exists no classical probabilistic polynomial time algorithm that on input of such an instance of the integer linear program finds an assignment of the variables which satisfies all the constraints. By the way, that's quite interesting, satisfies all the constraints. Basically was translated from being consistent with the sample. So it's a really nice reduction, but it's quite lengthy. Okay, so that satisfies all constraints, an assignment of all the variables that satisfies all the constraints, and approximates the optimal solution, the optimal cost by some factor here. So okay, here I wrote alpha greater than 1. So maybe to really get this, that it comes from the Occam's razor theorems, you can basically write here opt and then times opt to the alpha times the size of ILP to the beta, which we saw before, because here alpha is now bigger than 1, so we can just pull this out. And then we see again that this is this approximation task. Okay, and so we cannot find an assignment of the variables such that our cost function is smaller than this. But so there's no classical algorithm that can do that. But we can find a quantum algorithm that does this. We can basically find a quantum algorithm, a polynomial time quantum algorithm that an input of such an optimization task from this class ILP RSA finds a variable assignment that satisfies all constraints and for which the objective function is bounded as such. And this is what we show in the in our paper. So basically what we have now, we have the classical hardness. There is no polynomial time algorithm. and we have the quantum efficiency. There is a polynomial time algorithm, so we have the super polynomial advantage in this approximation task. And I mean, before I come to the conclusions, maybe to reason about why the what the quantum algorithm really is. Basically, we have Shor's algorithm to break RSA, and then we have this this RSA circuit. And if we have like input-output pairs, so what we get is basically a Y and these and also this E and the N, and then we can find by this using Shor's algorithm the D, the secret exponent, and if we have this, we can come up with this circuit again, and then we can run it through this whole reduction chain. Basically, all of these are polynomial reductions, so the size then of our assignments is then also polynomial. Sorry, not the size of our assignments, basically the size of our cost function. Okay, so for the conclusions, what we did is what's I think it's really nice about this. We did an end-to-end constructive proof. So you can like basically program this Boolean circuit that decrypts some RSA ciphertext, and then you can run it through the whole reduction, and you can then in the end have this integer linear program spit out. And now you know for these kind of problems, classically it must be hard to find a low cost here, but quantumly it is easy. So we have a constructive proof. It is an in-principle result, let's be honest. I mean, on the quantum side, we just have Shor's algorithm, so it's not that exciting. But it's one that was, but this in-principle result was dearly needed. We didn't have any like proof that there's an advantage for combinatorial optimization or a super polynomial advantage for combinatorial optimization problems. And now we know, okay, there is something. And so since this is constructive, maybe there might be some new insights that we can get from looking at these instances and look at, okay, where does the quantum advantage come in? Maybe it's yeah, I mean that's that would be kind of nice. And also maybe we can find like we can program it from end to end and then use like small instances as like a benchmark and say, okay, our quantum computer approximated this this ILP RSA problem pretty well, so our quantum computer does offer a quantum advantage. Okay, and with that, I would like to finish my talk and thank you for your attention and very nice questions. So are there any more questions?
Yeah, thank you again for the talk. Can you hear me, by the way?
Yes, yes, I can. Yeah.
Okay. So no one else has any more questions for a speaker?
I have a question. Maybe I missed the main point. I think you proved the classical harness by reduction of all these different concepts, but there are different things, and how's the global search can help to do the efficient algorithm. I didn't get which part you just.
You mean Shor's algorithm?
Yeah. Yes.
Yeah. So yes. So yeah. So what we get through for this task is we get this huge ILP, this huge integer linear program. Okay, now we want to approximate this with a quantum computer. So what we do now is we look at all of these constraints, and these constraints, what is basically there is through the reductions, we basically encoded this sample S of size m into all of these constraints here. And now we can read out from this the input-output pairs, so S. And if we are given S, sorry, so I'm jumping around a little bit. What S really looks like is these input-output pairs. So the inputs are this top line here. It's basically Y to the power of some of these different exponents, the public exponent E, and M. And once we have these inputs, using Shor's algorithm, we can derive D. Okay, and once we have D, what we can do, we can build this circuit that is pictured here. Right? If we know D, then we can build the circuit because we know the bits of D now. And once we have the circuit, we can run it through this whole reduction here, through all of these points. And this is how the reductions were like constructed, and then come up with a satisfying assignment that minimizes or that approximates the optimal size of our integer linear program. So it's really how these reductions are set up, that once you prove this reduction, you basically in the proof you already have a recipe of how to transform this Boolean circuit into like a satisfying assignment of this ILP.
Okay, I see. Thank you. So, what's the lesson learned for having this quantum advantage? What will you say about the lesson we've learned?
Sorry, I didn't understand the second part.
I mean, from your proof, what's the lesson we can learn for other insight to have to have quantum advantage? Yeah.
Yeah. So the message really is that there is a provably advantage. This is really what I mean with in principle. It doesn't really help us now to come up with new quantum algorithms to do combinatorial optimization tasks, because our quantum algorithm was really tailor-made to this problem. So, but the lesson really learned is, okay, we didn't in the beginning, we didn't really have any reason to believe that there is an exponential or a super-polynomial advantage. Now we do have a reason to believe, because we already showed it for one example. This is basically the lesson or the message.
I see. That's very cool. Thank you.
Yeah, you're welcome.
Okay. Do we have more questions? Okay. I think perhaps the audience is satisfied with your presentation.
Yeah, perfect. I guess it means I did a good job, I hope.
Yeah, it was a good presentation. So I think we can stop now.
Mm-hmm.
And I'm just going to stop the recording.
All right.